Imagine stepping out onto the surface of the sun right now. Not in a spaceship, not wearing some super advanced protective suit, but just you, standing there as if it were solid ground. The moment you appear, there isn't time to scream or react. In fact, there isn't even time to think. Because before your brain can register anything, before a single nerve impulse can make it from your skin to your spinal cord, you've already been annihilated. We're talking about a billionth of a second, 1 nanosecond, and in that unimaginably tiny sliver of time, your body doesn't just burn, it ceases to exist in any recognizable form. Surviving for a nanosecond on the sun isn't a question of strength, bravery, or technology. It's a question of physics, and physics doesn't negotiate. Let's start with what you'd be up against. The sun's surface, called the photosphere, has an average temperature of about 5,500 degrees Celsius. That's 10 times hotter than molten lava and hot enough to melt steel like ice in a bonfire. But the number barely scratches the surface of what's happening. At that temperature, the radiant energy isn't just hot air. It's a constant, blistering flood of photons, light particles, that slam into matter with devastating force. The amount of energy leaving each square meter of the sun's surface is about 63 million watts. Imagine placing your hand on a spot of ground where 6,000 nuclear bombs are exploding every second, and you're still not even close to the reality. So what happens to you in that first nanosecond? To put it bluntly, you don't burn. Fire as you know it needs time. On Earth, when you touch a hot stove, heat travels through your skin, molecules vibrate, cells are damaged, nerves fire, and your brain screams, ouch. That process takes milliseconds, thousands of times longer than the moment you're granted on the sun. On the sun, there is no slow cooking. Your body absorbs so much energy so quickly that the bonds holding your molecules together break instantly. Proteins unravel, water molecules split, and electrons are ripped from their atoms. You don't just roast, you are ionized, converted into plasma, the very same state of matter that makes up the sun itself. To understand the speed of this destruction, let's crunch some numbers. The average surface area of a human body is about 2 square meters. Each square meter of the sun is blasting out 63 million watts, so your body absorbs about 126 million joules of energy every single second. That's the equivalent of about 30 kilograms of TNT detonating on your skin each second. But you're not there for a second, you're there for a nanosecond, 1/1000th of that time. In that instant, you still absorb roughly 0.126 joules. That doesn't sound like much, less energy than a falling raindrop. But here's the catch. That energy isn't spread over time, it's delivered in a pulse so concentrated that it strikes directly at the atomic bonds holding you together. It's like being hit by a billion microscopic bullets simultaneously, each one tearing through matter with no mercy. To make it more vivid, think about how fast chemical bonds break. When scientists use powerful lasers to study molecular vibrations, they find that a single chemical bond can snap in femtoseconds, a billionth of a second, a millionth of a. That means your atoms start falling apart well before that nanosecond has even finished ticking by. The nanosecond isn't your chance to survive. It's already long enough to be dead several trillion times over. It's also massive. But the sun isn't just hot. Its gravity is 28 times stronger than Earth's. If you could somehow stand on the surface, never mind the fact that it's gas and plasma with no solid ground, you'd feel yourself weighing almost 3 tons. Every bone in your body would be crushed instantly under that pressure, assuming you still had bones left after the heat and radiation. And as if that weren't enough, you'd also be slammed by a constant stream of high-energy particles. Electrons, protons, and ions traveling at hundreds of kilometers per second. It's like standing in the middle of a machine gun firing plasma bullets from every direction. Now you might be thinking, but what if, somehow, you had a magical suit? Some kind of shield that kept the heat away? Could that let you last for 1 nanosecond? Unfortunately, no. The problem isn't just temperature, it's the sheer intensity of radiation. The photons alone, each carrying packets of energy, would be enough to tear through any known material. And if the photons didn't get you, the constant bombardment of particles would. Even the strongest metals, the most heat-resistant ceramics, the most advanced theoretical materials we've ever imagined, they would vaporize instantly. In fact, some would fail even faster than your skin, shattering under the stress of radiation pressure before the nanosecond is up. Let's zoom in even further, down to the atomic level. Imagine 1 molecule of water inside your body. At normal Earth conditions, that molecule sits happily, 2 hydrogens and 1 oxygen sharing electrons in a stable bond. Place that molecule on the sun, and the incoming photons hit it with such force that the electrons are stripped away instantly. The molecule doesn't just heat up, it ceases to be water. The hydrogens and oxygens split, the electrons scatter, and within femtoseconds you no longer have a molecule at all. Now multiply that by the roughly 7 octillion atoms in your body, and you start to see the scale of what happens in that brief nanosecond. All falling apart in unison. If you wanted to capture this in slow motion, imagine watching your body dissolve into a storm of glowing particles. First, your skin peels off not as ash, but as a glowing mist of ions. Then your muscles, bones, and organs follow, not burning away like wood in a fire, but erupting outward as plasma. Within an instant, all that remains of you is a tiny cloud of gas and dust, swept away by the constant outflow of the solar wind. And because the sun is constantly ejecting matter into space, your remains would be gone almost instantly, carried off as just another puff in the endless solar storm. But maybe you're wondering, what about awareness? Would you feel anything? The short, brutal answer, no. The nervous system operates far too slowly to compete with the forces at play here. The fastest nerve impulses in your body travel at about 100 meters per second. To feel a sensation, your nerves need to fire, transmit the signal to your brain, and then your brain needs to process it. That takes at least a few milliseconds. But you don't get milliseconds on the sun. You don't even get microseconds. By the time the first nerve ending in your skin even starts to fire, your entire body has already been reduced to plasma. So in one sense, there's a kind of mercy here. You wouldn't have time to experience pain. You wouldn't even have time to know what happened. You'd simply be erased. And the scale of this erasure is enormous. On Earth, we think of dying as something that happens to an individual, a body. On the sun, your destruction is indistinguishable from the background processes happening constantly. Every second, the sun fuses about 600 million tons of hydrogen into helium, releasing energy on a scale we can barely comprehend. Against that backdrop, the complete disintegration of one human body doesn't even register. You're less significant than a spark in a wildfire. In fact, you become the same thing the sun is made of, plasma, lost in the endless sea of heat and light. Yet this raises a fascinating thought experiment. How does the energy released by your destruction compare to the sun's own output? If your body contains about 70 kilograms of mass, Einstein's famous equation E equals mc squared tells us that if all of that mass were converted directly into energy, you'd release about 6.3 times 10 to the power of 18 joules. That's an enormous number, comparable to a billion Hiroshima bombs. But the sun emits 3.8 times 10 to the power of 26 joules every second. So even if you somehow went out in a blaze of complete matter-to-energy annihilation, your contribution would be less than 1/1,000,000% of what the sun does naturally in the same instant. To the sun you're nothing. Just background noise. Still, the idea of lasting even a nanosecond on the sun remains intriguing because it forces us to think about what time means at such extreme scales. On Earth, a nanosecond is irrelevant. Nothing in our daily lives happens that fast. Your eyes blink in about 1/10 of a second. A hummingbird flaps its wings at about 50 times a second. Even the fastest supercomputers we build measure their speeds in nanoseconds, but to us, those speeds are abstract, not physical. On the sun, a nanosecond isn't trivial, it's more than enough for absolute destruction. It's a unit of time where reality shifts, where the ordinary rules of survival collapse. So could you survive a nanosecond on the sun? Not a chance. Physics doesn't bend and the sun doesn't wait. 1/1000,000th of a second is long enough for every bond in your body to break, every cell to vaporize, every atom to scatter. In the grand scheme of the cosmos, your attempt wouldn't even be noticeable. But the deeper question, the one worth exploring, is what happens if we keep pushing this thought experiment further. What if we ask, could anything at all, any material, any technology, any future invention, last a nanosecond on the sun? And what if, instead of surviving, we think about what would happen to the fragments of matter you leave behind? Where would they go, and what story would they tell as they become part of the sun itself? Let's push the question further. We already know that a human body can't last a nanosecond on the sun, but what about anything else? Could some miracle material, some invention of the future, withstand that furious blast of radiation and heat for 1/1000,000th of a second? Let's imagine we build the strongest shield humanity can conceive, maybe layers of tungsten, ceramics, carbon composites, the kind of materials we use on spacecraft heat shields. Could we buy ourselves that nanosecond? The problem is all known materials break down at far lower temperatures. Tungsten, the metal with the highest melting point, collapses at around 3,400 degrees Celsius, barely a bump compared to the sun's 5,500 degrees. Carbon composites do better at first, but even they start to vaporize quickly under intense radiation. And ceramics? They'd shatter like glass dropped in a volcano. In truth, the sun isn't even trying. It's not throwing flares, it's not erupting with extra violence, it's just existing, and that alone is more than enough to erase anything we can currently make. What if we imagine some hypothetical material that could survive, something beyond human technology, maybe forged in the hearts of neutron stars? Even then we'd still face the problem of radiation. The sun emits a constant stream of high-energy photons across the electromagnetic spectrum, from harmless-looking visible light to searing ultraviolet and bone-crushing X-rays. Even if the outer shell of our magical shield could survive the heat, the radiation would pass straight through, bombarding everything inside. X-rays and gamma rays have no respect for walls. They pass through most matter like it's tissue paper. The only way to stop them is with immense thicknesses of lead or other dense metals, but even that wouldn't hold against the sheer flux of radiation pouring out of the sun. It would be like trying to stop a waterfall with a sponge. You might block a drop, but the flood destroys everything anyway. And then there's gravity. If somehow your shield could keep you cool and block the radiation, the sun's gravitational pull would still crush you. On Earth, a person weighing 70 kilograms exerts about 700 newtons of force on the ground. On the sun, that same person would weigh nearly 2,000 kilograms. That's like carrying the weight of a small car on your shoulders while also being blasted by an endless furnace. And unlike Earth, where you can stand on solid ground, the sun is plasma, a soup of ions swirling chaotically. There's no surface to stand on, only layers of gas and boiling convection currents. Any shield or platform would simply sink, dragging you into hotter and hotter layers where survival isn't just impossible, it's unthinkable. But let's flip the question on its head. Instead of asking whether you could survive, let's ask, what happens to you after that nanosecond? Where do the fragments of your body go? In that instant, you're converted into plasma, a mixture of ions and electrons. Those particles don't just vanish. They become part of the sun itself. Your hydrogen atoms, which make up most of your body, are indistinguishable from the sun's own hydrogen. Some of them might drift outward, carried away in the solar wind, traveling across the solar system at hundreds of kilometers per second. In a few days they could pass by Earth. In a few months they might reach the edge of the solar system. In tens of thousands of years, those particles could be halfway to another star. So in a strange way, a part of you does survive, not as a living being, but as free-floating atoms scattered across the galaxy. Some of your atoms might go the other way, sinking into the sun. There, over millions of years, they could be pulled deeper into the core. If enough hydrogen atoms from your body made it there, they'd eventually take part in nuclear fusion. Imagine that, the very atoms that once formed your skin or your blood cells becoming fuel for the sun itself, fusing into helium and releasing energy that streams outward as sunlight. And maybe, just maybe, photons born from those reactions might travel across space, fall onto Earth, and light up a future sunset. In that sense, your nanosecond on the sun might contribute to someone's moment of beauty centuries later. It's humbling, isn't it? On one hand, you are utterly insignificant compared to the sun's power. On the other, the universe recycles everything. Even your annihilation becomes part of the endless story of energy and matter flowing through the cosmos. You don't get to survive the nanosecond, but you do get to participate in the sun's life cycle in your own small way. Now let's take another angle. What if instead of a person we drop something artificial onto the sun, say a smartphone? Could your phone survive a nanosecond longer than you? Not really. The plastic casing would vaporize instantly, the glass would shatter into plasma, the lithium battery would explode violently, and the circuitry would disintegrate before a single transistor could switch. In fact, the phone might go even faster than your body, since it has smaller, thinner structures that heat up quicker. And even if it could survive the heat, the sun's radiation would scramble the memory and fry the circuits instantly. So no, your phone doesn't fare better than you do. It just dies differently. Let's make it bigger. What if we dropped an entire building or even a mountain? The same story plays out, just at a larger scale. The surface matter disintegrates instantly, vaporized into plasma. The rest sinks into the convective layers, churning violently, breaking apart, spreading out, and eventually becoming indistinguishable from the rest of the sun's mass. It's like throwing an ice cube into a furnace. You can make the cube bigger, but it doesn't matter. The furnace wins every time. Even spacecraft aren't immune. NASA's Parker Solar Probe is currently flying closer to the sun than any spacecraft in history. It carries a heat shield designed to withstand temperatures of 1,400 degrees Celsius, which is impressive, but still nothing compared to the sun's surface. The probe survives not by touching the sun, but by skimming close, moving fast, and avoiding the densest regions. If it were to dip into the photosphere even for a nanosecond, it would be gone instantly. The heat shield would vaporize, the instruments would melt, and the craft would dissolve into plasma. The probe survives by respecting distance, not by brute force. So what's the lesson here? It's that the sun exists on scales that make our daily experience meaningless. Time, as we live it, is slow compared to the physics of the sun. Heat, as we know it, is gentle compared to its fire. Gravity, as we feel it, is a toy compared to its pull. And yet, we live thanks to this star. The same sun that would destroy you in a nanosecond if you touched it is the same sun that warms the earth, drives our weather, fuels our crops, and makes life possible. At 93 million miles away, the sun is our friend. Up close, it's an executioner. So could you survive a nanosecond on the sun? The answer is simple. No, and not just no, but absolutely not, not in any way imaginable. Not you, not your body, not your technology, not even the best materials we can conceive. The sun is not survivable even for the tiniest fraction of time. But that doesn't make the question pointless. In fact, it makes it fascinating. Because by asking it, by imagining what would happen, we learn just how extreme the universe can be. We see how fragile human life is, how powerful physics is, and how our existence depends on the delicate balance of being just far enough away from our star. And maybe that's the deeper point of this whole thought experiment. The universe is not built for us. It doesn't bend to our needs, it doesn't adjust to our scale. Yet within this vast, uncaring machinery of stars and gravity and plasma, life on Earth exists. You exist. You're made of atoms forged in stars long before the sun was born. And while you can't survive a nanosecond on the sun, you can survive decades here on Earth, in the thin, miraculous shell of conditions that keep us alive. In that sense, maybe the real miracle isn't surviving the sun, it's surviving anywhere at all. So the next time you look up at the sky and feel the warmth of sunlight on your skin, remember this: that warmth is a gift. At the right distance it sustains you. Up close, it erases you in an instant. The same star that would obliterate you in a billionth of a second also paints your mornings gold, charges your solar panels, and grows your food. It is at once the most hostile and the most generous object in your life. Survive on it? Never. Thrive because of it? Absolutely.